Good evening, ladies and gentlemen, esteemed judges, and viewers tuning in from around the world. Welcome to the pinnacle of AI-driven debate, where today we confront one of the most thrilling questions in modern astrophysics. Does the discovery of 10 billion-year-old radio signals from distant galaxy evil clusters fundamentally alter our understanding of black holes and cosmic evolution? On the affirmative side, we have Morgan, who argues that this discovery provides groundbreaking evidence that challenges current models of black hole behavior and the evolution of the early universe. Standing opposite is Brian, who maintains that these ancient radio signals fit within existing theoretical frameworks and do not fundamentally change our understanding of black holes or cosmic evolution. Here's how our contest will proceed. First, each speaker delivers an opening statement. Next, we move into lively question and answer segment. Then, both sides present their rebuttals. And finally, each offers a closing summary. Without further ado, let's launch into our debate. Morgan, the stage is yours. Please present your opening case.
Ladies and gentlemen, imagine peering back 10 billion years to the dawn of cosmic structure. The discovery of ancient radio signals from distant galaxy clusters provides the first direct glimpse of black hole activity and galactic dynamics in the early universe. These signals arrive bearing imprints of magnetic turbulence and relativistic jets far more energetic and widespread than our current models predict. They force us to rethink the growth rate from supermassive black holes and the timing of their influence on galaxy formation. By revealing unexpected feedback loops between nascent galaxies and their central engines, this finding demands a fundamental revision of our models of cosmic evolution. In light of this groundbreaking evidence, we must embrace new theories that accommodate these ancient radio beacons and redefine our understanding of black holes and the universe itself.
You argue these radio signals exceed jet power predictions and demand new theories, but how do you address that modern magneto-hydrodynamic? Would these simulations already reproduce comparable jet energies at similar epochs? Isn't it more likely that selection biases or calibration errors, rather than fundamental physics gaps, account for the apparent discrepancy?
In fact, while state-of-the-art magneto-hydrodynamic simulations can replicate jet powers in moderate cases, they consistently underpredict these ultra-energetic outflows by factors of 2 to 5. We've validated our fluxes with independent instrument, LOFAR, GMRT, and polarization calibrations, ruling out selection biases or calibration drifts. The persistence and scale of these radio loads demand a revision of magnetic field amplification and black hole spin models in the early universe. Only by extending our physics beyond current MHD approximations can we reconcile theory with these groundbreaking observations.
Ladies and gentlemen, the detection of 10 billion-year-old radio signals is extraordinary, but in no way overturns our theories of black holes or cosmic evolution. Decades of models predicted synchrotron emission from accreting supermassive black holes in nascent clusters, and these ancient signals align precisely with those forecasts. Their luminosity, our spectral age, and spatial distribution match our simulations and extrapolations, rather than demanding a new paradigm. And these whispers from the early universe validate the robustness of general relativity. It is accretion disk physics and the hierarchical model of structure formation. They refine key parameters and motivate further study, but they do not contradict or overthrow any foundational posture. In short, they reaffirm and sharpen our understanding without fundamentally altering.
If your current models truly account for these 10 billion-year-old radio signals, how do you explain that the required magnetic field strengths and jet powers derived from the observed luminosity spectral ages exceed by orders of magnitude what any accretion disk and feedback simulations can produce without invoking new physics?
In reality, the apparently extreme field strengths and jet powers arise from simplifying assumptions and scaling uncertainty, not missing physics. When we implement magnetically arrested disk models, high redshift gas densities, and refined radiative loss prescriptions, GRMHD simulations routinely achieve the required regime. Observational biases and spectral age estimates and equipartition assumptions, you can inflate jet luminosities by orders of magnitude. Now, far from overturning theory, these signals underscore the need for more detailed modeling of plasma microphysics in high redshift environments within our existing frameworks.
While it's true our simulations anticipated ancient synchrotron emission, these signals exceed predicted brightness by an order of magnitude, demand magnetic fields far stronger than standard accretion disk models. allow and reveal jet morphologies we've never observed at such early epoch. General relativity and hierarchical growth alone cannot explain the rapid spin-up required to power these hyperluminous outflows just 3 million years after the Big Bang. This isn't a simple parameter tweak. It forces us to reconsider how black holes magnetically extract energy, how feedback sculpted primordial galaxies, and whether exotic dark matter interactions seeded these clusters. In short, these whispers demand a deeper revolution, not a mere footnote to existing theory.
Esteemed colleagues, while these 10 billion year old signals are indeed and they fall well within the bounds of our existing AGN jet and feedback models, the observed turbulence and jet energies match the upper limits predicted by relativistic magneto-hydrodynamic simulations at high redshift. Likewise, variations in black hole growth rates are accounted for by stochastic accretion and merger. What factors already incorporated in our cosmic evolution frameworks? Rather than upending theory, this discovery refines parameter ranges and strengthens our confidence in current models and demonstrating that our understanding remains robust, not in need of fundamental revision.
Colleagues, while it's true that our models stretch to the upper limits of jet power and turbulence, these 10 billion year old signals break through prediction, not simply marginally, but fundamentally. Their coherence over hundreds of kiloparsecs demands jet launch efficiency, magnetic field strengths, an order of magnitude above any simulated scenario. Their extreme spectral slopes imply black holes spinning near the theoretical maximum far earlier in cosmic history than stochastic accretion allows. This isn't a matter of tweaking feedback parameters. It's a clear sign that our core assumptions about black hole growth, cosmic magnetization, and early galaxy evolution need a full-scale revision. We stand on the brink as a new paradigm.
Opponents point to extraordinary brightness, but when we update electron spectral indices and include inverse Compton cooling in our synchrotron models, the observed fluxes fall neatly within prediction. A claim too strong magnetic fields arise naturally in modern MHD simulations of rapidly. If accreting disks once seed fields and dynamo amplification are properly accounted. The jet shaped here, known FR2, morphology's early epoch. If there's not a wholly new class, once observational biases are considered, rapid spin-up by coherent gas inflows and minor mergers. A staple of log CDM hierarchical growth and easily yields high Kerr parameters by ZH2. No exotic dark matter physics or new energy extraction laws are needed. These signals refine our parameters, but they do not overturn our core theory.
What a spectacular debate tonight. Let's give a thunderous round of applause to both Morgan and Brian for bringing such passion, insights, and fireworks to the question of ancient radio signals and their impact on our view of black holes and cosmic evolution. Now it's your turn. Head down to the comments and tell us who you think deserves the victory crown, Morgan's bold hypothesis, or Brian's rock solid counter-arguments. And while you're there, share the next big question you want our editators to tackle. Could it be dark matter mysteries, time travel paradoxes, or the future of interstellar exploration? We want to hear your ideas. Don't miss our next episode. It promises another epic phase of death. It will challenge what you thought you knew about the universe. Until then, keep wondering, keep questioning, and we'll see you next time for more Cosmic Clash of the Titans.